In this lesson, we're going to be talking about image acquisition for both direct and indirect digital X-rays. We're going to cover two types of indirect acquisition and one type of direct acquisition. So first, we're going to talk about the indirect CCD or charge coupled device. This method uses a CCD to collect the light that is created in a very similarly to some CR setups where light is created and gathered by a CCD. The difference, of course, with a direct and indirect X-ray is that there is no plate, there is no processor. Everything is done right as you expose the plate. Everything is done either wirelessly or through the Bucky, or some older systems even had wired plates. Newer systems, though, the free form plates are generally wireless and they operate using the hospital Wi-Fi system. So when we talk about the charge coupled device, it performs the function of transforming the light into the electric signals. So it's going to be attached under the scintillating screen. Now, the scintillator for indirect, both CCD and for the flat panel detectors, the scintillator does not change. It is cesium iodide, and that's a fact that you want to remember. And cesium iodide's job is to convert X-rays into light. Then fiber optic cables or some sort of lens array or something to that effect carry the light, some sort of light guide takes the light to the CCDs. And one of the drawbacks of this method is that you need multiple CCDs, which are expensive, and the bigger they are, the more expensive they are and harder they are to make. So the seams where the CCDs come together, for example, can cause problems, and information has to be interpolated or gathered from surrounding pixels so that those areas don't show up on the film. Or the image, I should say. It's more correct terminology to say image since it isn't a film. Now, the CCD cameras then take that newly created signal and send it to the analog to digital converter. Once you get to the analog to digital converter, it really doesn't matter where the signal came from. The next steps are all going to be the same. And we'll cover that in a different study guide. So each CCD is made up of millions of pixels. So in the case of the charge coupled device, this is where your pixels are going to come from, and all of these pixels are going to get light from the light that's created in the scintillator. So the pixels in this method, one of the advantages is that they can be very small. 100 by 100 microns is about 5 line pairs per millimeter, which is pretty good spatial resolution. One disadvantage is because of the way that the light is gathered and sent to the charge coupled device, that initial image is actually demagnified to fit the CCD array, and that does cause a loss in image quality. Okay, the other type of indirect is the thin film transistor or flat panel indirect. Now, this uses a photodiode layer to convert light to electrical signal. And then you have thin film transistors, sometimes called a matrix array or TFT array. And this photodiode layer that's right on top of that is usually amorphous silicone. And then above that is the scintillator, which is cesium iodide. And we'll go through the process step by step here in a minute so you can kind of get an idea of how you should be studying it, which I will always encourage you to study it in the way that it happens. So the cesium iodide crystals, similar to the phosphor crystals in CR, are packed in that needle-like columnar shape to reduce light scatter and improve spatial resolution. So when you're looking at a digital X-ray Bucky or a digital X-ray plate, what happens first in indirect is that X-rays are going to hit first that scintillator layer, which is cesium iodide, and be converted into light. The light is then converted to an electrical signal by the photodiode layer, which is amorphous silicone. Okay, then that signal is going to go through those TFTs sent to the ADC to be digitized and processed. Now, if this were a charge coupled device, it would start the same. The X-rays would hit the cesium iodide, convert to light, and then the light would be sent to the CCD, and that's where it would be converted to electrical signal and then sent on for processing. So you have some different materials in the flat panel, and the major difference is those thin film transistors, which we'll talk about in a minute. So X-rays to scintillator layer to photodiode layer, and then briefly held in those thin film transistors before they're read out in order. So when you're talking about these systems, and this applies to direct TFT as well, if there's a thin film transistor involved, and that's what's going to momentarily hold the analog signal as it's being read out in order, then each actual physical thin film transistor represents 1 pixel. So the limitation in digital on the pixel size is an actual physical piece of machinery that is exactly the size of each pixel. So the smaller you can build those, the smaller your pixels can be, and the better the spatial resolution. Okay, and that applies to any acquisition method that uses a thin film transistor, which is indirect TFT, and then there's a direct version as well, sometimes referred to as flat panel detectors. So when we look at direct thin film transistor or direct flat panel, no light is created. That step is skipped. Be very careful of the vocabulary here. It is very close. It is very similar to indirect TFT. We're not using a photodiode here. We're using a photoconductor. So the X-rays are going to strike amorphous selenium, which is a photoconductor. Don't confuse that with amorphous silicone, which is the photodiode in indirect. Make sure you keep that straight. And then that amorphous selenium photoconductor layer is attached to the TFT array. The reason we use selenium is it provides good spatial resolution and it has a good DQE. In other words, it detects X-rays well. So as X-rays strike the photoconductor, there's basically an electric field which is applied to the selenium, and this simply is to help make sure that the electrons, the signal that we want, is moved into the TFTs for momentary storage and processing, right? They're only there briefly. So the incoming X-ray photons, they hit this amorphous selenium. There's a voltage applied across the top which helps to guide them down into these thin film transistors, where they again are momentarily stored and immediately read out in order, and then the image of course comes right up on the screen. So there's no processor or cassette processing like there would be in CR. So to review your indirect TFT systems, X-rays hit the scintillator layer, which is normally cesium iodide, and change it into light. The photodiode layer, which is amorphous silicone, and then the matrix array is underneath that. So they hit the scintillator first, then the photodiode, then the matrix array. The photodiode layer is responsible for changing the light into the electric signal, which is then collected and read out by the thin film transistors. And again, there's a lot of different ways to say that. The matrix array, the thin film transistor array, the TFTs. So be on the lookout for a lot of different words that are basically in reference to the matrix. So when we're talking about image quality and spatial resolution and matrix and pixel size, when you're thinking of direct systems, that corresponds to an actual physical piece of machinery, which is a single individual thin film transistor, sometimes also called a detector element, or DEL. That's more vocabulary that you definitely want to know. Now, also remember for indirect that a charge coupled device can be used, which will also change light to electric signals. So there are 2 different indirects that we covered. The direct system uses the photoconductor amorphous selenium. So X-rays strike the photoconductor, which turns them directly into the electric signal. We apply a current across that to guide that signal down to the thin film transistors below, and then again they're read out and sent for processing. So let's talk a little bit about the thin film transistors so you understand what they are. The thin film transistor array is your matrix. It's a matrix of detector elements. They each represent a single pixel. So it's arranged just like we would talk about spatial resolution on a monitor. It's a matrix of rows and columns, and then the TFTs, as I mentioned before, collect the signal and read them out in order. So the components of each microscopic TFT is the sensing and storage area, and then there's a piece of it that is devoted to the electronics required to run it. So the TFTs essentially are switched on, and then they know that row then knows it's that row's turn to be read out. This is what keeps the image in order. Otherwise, it would come out on the screen like a scrambled puzzle, basically. So if you imagine these are the TFTs, they have their sensing and storage area, and then they have the electronics that actually run the TFT. And when they get a certain voltage applied, this row would then activate and then go out to the ADC, so everything is kept in order. Now, the sensing storage area, this is an important fact you must know for the exam. It's called the fill factor. So when you're looking at those pictures, not all of the pixel is actually devoted to sensing and storage. There's that little bit that's devoted to actually running it. So the fill factor is the percentage that is devoted to sensing and storage. So as you can see by the example here, 80% fill factor means that the other 20% of the space is taken up by electronics used to run it. Okay, so the higher the fill factor, the better contrast and better spatial resolution you'll have. And you can see why this limits us from making them smaller. It's not worth building the TFT smaller unless the fill factor remains the same or better. Because if the fill factor goes down too much, you're not actually helping yourself by making all of the electronics smaller. So the fill factor is important. It's sort of the usefulness. What percent of it is devoted to creating the image and what percent is devoted to electronics? And again, the process of switching them off is simply row by row so that they're read out in order. Okay, so that's going to do it for this lesson. We will cover modulation transfer function in a future video guide regarding spatial resolution. But hopefully that was helpful so that you understand image acquisition for indirect and direct digital X-ray. If you have any questions, you can feel free to email me as always. And of course, use your ARRT content specifications when you go to prepare for your ARRT exam, and make sure that you're studying all the digital items located on it.